Swayam Prabha. Digital India. Educated India.
So, good morning to all of you. This particular topic of the basic principles of spectroscopy is a course that I have already given under the NPTEL project. NPTEL, I have given a number of courses, and I want to show you by sharing my screen. Okay, I share my screen now. Okay, here it is. Okay, you look at the full screen. The nptel.ac.in is the website which contains more than 3,000 courses of chemistry, physics, engineering, arts, science, commerce, and all those areas. And there is this NPTEL online course, NOC. There is a course chemistry 2 and chemistry, this one, the spectroscopy, introduction to quantum spectroscopy. Chemistry 2 is analytical spectroscopy course. It's not chemistry and biochemistry, but that's a discipline. But the course is spectroscopy. So there is a lot of lectures in this course. Okay? You can also read them, you can download them, and you can also write to me if you do not know or you have doubts about some of the aspects. Okay, that's one thing. The second I wanted to show you is, let me move out of the screen. Okay. The second is that today I shall talk about a few things, basic aspects of spectroscopy, and generally in any spectra there are three properties that we need to understand. For example, if you go to the spectrum here, what you see here is an example of an IR, infrared spectrum of benzene molecule. And you see a plot of wave number as the x-axis, and the transmittance, or it's the intensity of the spectral profile. So you can see that there is a line, or there are lines in this region between 3000 to 3200 centimeter inverse. This is wave number inverse, centimeter inverse. And then you can see there is a small line, there is another line, there is another, and so on. So these are basically specific to transitions or line positions. Each line position gives a representation of a transition and the spectral frequency that the radiation is absorbed by the molecule. So here, there are many such lines. There are big lines and there are small lines, and you can see. So the first one is positions, one here, one here, one here, one here, and so on. The second property is what is called the line intensities. The line intensities refer to the area under a given peak. So for example, the area under this peak, subject to some baseline here, area under this peak, you see that these areas are different for different transitions. So these mean that the line intensities, which are due to the number of molecules undergoing transition, they are different, which tell you that the population of molecules corresponding to this energy level transition is different from the population of molecules corresponding to this energy level or this energy level or this energy level. So the line intensities tell you about the statistics of the molecular populations. how many molecules are in one excited state, one vibrational state, how many are in another vibrational state. So it is a statistics, the number. So the population density is approximately represented by the line intensities. Okay. The line positions, of course, give you transitions, specific transitions corresponding to the change in the energy level from the lower energy to the higher energy, and the difference is this particular frequency. What is the third one? The third one is the line width. This is an extremely important phenomenon. Now, if you look at line positions, this is understood by quantum mechanics. If you want to study line intensities, it is both quantum mechanics and statistical mechanics which will give information about the line intensities. We have to use statistical mechanical theory and also quantum mechanical theory to understand the line intensities. Line widths are very dynamic phenomena. What exactly are those? See, you can see that. This particular line is a broader line. This is even broader line. It has a, and then you can see a very short line here, but you can see a very broad line here. So the broadening of spectral lines is a necessity by quantum mechanics. There is a minimal broadening called natural line width, which corresponds to what we call as the minimum breadth of any spectral transition. And the line broadening is due to not all molecules having the same energy and transferring their energies by absorbing the electromagnetic radiation to a higher energy state. All of them do not have exactly the same energy state, but they are spread around that energy state by a small width. And the spreading happens because the molecules are not static. They are not stationary. They undergo collisions among themselves. They undergo collisions with the medium. For example, if you take the gas-phase molecules, apart from the molecules, there is the inert gas, and there is the oxygen gas, there is air and other things. Therefore, the molecules undergo collisions with them. The collisions change the molecular energies by a small amount, and those changes are reflected in the line broadening. One is called the collisional broadening. The other is the molecules themselves are moving at any temperature above 0 Kelvin. They have a velocity, and therefore as the molecules are moving, when they emit radiation, the emitter radiation has a slightly different frequency than if the molecule is stationary. This is called the Doppler line width. Okay. So the natural broadening, the Doppler broadening, the collision broadening or pressure broadening, these are all various phenomena which happen live, dynamic, when you are actually measuring the spectrum. To understand the line broadening is the most complex problem in spectroscopy, and it requires very, very advanced quantum mechanical as well as semi-classical theories to follow. We will not do any of that in this introductory lecture, but it's important to recognize that there are three features: the positions, the intensities, and the line widths, which need to be explained for each and every spectrum, each and every domain, whether it is microwave spectrum, or whether it is infrared spectrum, or whether it is electronic spectrum, or X-ray photoelectron spectrum, whatever. Each region has certain characteristics, but these three components are there for every region. Okay? So this is the first thing that you need to keep in mind, that the spectroscopy, which is the mother and father of quantum mechanics and all modern theories, the spectroscopy is complex in nature, but it is understood by properties that we can measure, properties that we can calculate in different regions. Exactly what is meant by the different regions. Let me open up a PDF file and see if I can show that clearly. Just one moment, please. Yeah. So here are two or three things. I hope you are able to see this whole screen. Are you? யாராவது கொஞ்சம் சத்தமா ஏசுன்னு சொல்லுங்க. இந்த ஸ்கிரீனை கிளியரா பார்க்க முடியுதா உங்களால? ஹலோ? கேக்குறதா? சரி, okay, fine. You can see that spectroscopy is determined by the spectroscopic properties are studied under various energies. You see, cosmic radiation has a very, very high frequency. Increase the size. Sorry, just a second. Yeah, cosmic radiation. See, very, very high frequency. And you know, frequency and wavelength are inversely proportional to each other. So if it is a very high frequency, then it is a very low, very short wavelength. And frequency and wave number are proportional. The proportionality constant is the speed of light. Wave number multiplied by the speed of light gives you frequency. So you can see that wave number and frequency are proportional. They are inversely proportional to wavelength. Cosmic radiation, very, very high frequency. We don't do much spectroscopy there, but we see radio astronomy and other areas of spectroscopy. We try to analyze the radiation that comes from outside of the terrestrial region. Then we have gamma rays, fairly high energy, gamma ray spectroscopy, and there is also mass Bayer spectroscopy. You can see that the frequencies are in the range of 10 raised to 20 hertz to 10 raised to 18 hertz. Quite a lot of it. And wavelength is, of course, inversely proportional to that. Frequency into wavelength gives you the speed of light. Okay, therefore you can see that this frequency and this wavelength relation is speed of light divided by frequency gives you wavelength. And wave number is proportional. Then you have X-rays, slightly lower in energy, ultraviolet rays, even lower in energy, visible radiation, all of us are very familiar with. And for visible alone, you can see that there is a smaller table here for ultraviolet, near ultraviolet, visible, near infrared, mid-infrared, far infrared. We can normally see between 8 to 8,000. You can see that here it is about the wave numbers is 3,000, 30,000 wave numbers to 10,000 wave numbers that you have here. The visible light, this is the spectrum that you see here. Okay? This is the region. This is a very narrow region in the whole of spectroscopy. See, the whole of spectroscopy from cosmic to radio wave is a very large region, but visible region is a very small region. And then you have infrared radiation, approximately terahertz frequency, and then microwave, you have gigahertz to thousands of gigahertz frequency, and then radio wave. Radio wave spectroscopy is usually magnetic resonance spectroscopy, and microwave also borders on magnetic resonance, except that this is electron paramagnetic resonance, whereas radio wave, much of the spectroscopy that we do is a nuclear magnetic resonance, which I will talk about tomorrow. Okay, so these are the various regions, and in each of these regions, if you look at it, the properties which we study, radio frequency in magnetic resonance spectroscopy, one is nuclear magnetic dipole, one studies the magnetic dipole interaction, one studies the spin coupling, which you probably had the first introduction by Professor Sankaraman in lecture 1, if we talked about spectroscopy. And then we have electric properties called the quadrupole and the other moments. These are studied under radio frequency region. This is magnetic resonance spectroscopy. From microwave to gamma ray, this is all optical spectroscopy. And you can see that microwave region studies rotational phenomena. Microwave spectroscopy is useful in getting the equilibrium structure. We can get the molecular electric dipole moment fairly accurately, and also the electronic magnetic dipole moment and all those things. Microwave spectroscopy gives you information about that. The infrared spectroscopy gives you information about the molecular force constants between the bonds, the bond force constant, the bond strengths, and molecular polarizability. That is, what happens to the molecule when you put it in an electric field? The molecule sort of distorts a bit. If it is a slightly weakly bonded molecule, it distorts a lot. So we say the molecule is more polarizable or less polarizable depending on the rigidity of the molecule. If the molecule is rigid, it's more polarizable. If the molecule is rigid, it's less polarizable. The concept of polarizability is understood. It leads to Raman spectroscopy. I don't know whether we have the time to look at it. Then UV visible region talks about and gives information on electric dipole moments, the electronic dipole moments, dissociation energies, and the three properties of excitation, luminescence, and fluorescence, and phosphorescence, these properties. Professor Mishra today probably will talk a lot more about some of these things, both qualitatively and quantitatively. Then we have the X-ray region, which talks about, which gives information on core electron spectroscopy. That is, if you think about sodium, the basic excitation happens by the valence electrons in electronic spectroscopy. The core electrons in the sodium, namely the 2s, 2p, and 1s electrons, it's very difficult to excite them. You need an extraordinarily large amount of energy. You can see that X-ray provides that kind of energy. To study the core electron energy transitions, and also in solids, the surface properties and characterization, because the X-ray has beautiful interactions with atoms in a regular solid. Gamma ray region gives you information about the chemical shift that you are familiar in NMR spectroscopy, or it's also called the isomer shift. And then the nuclear quadrupole moment, all these six nuclear properties and nuclear, the spin moments information can be obtained from the gamma ray region. So the idea is that spectroscopy is such a large area and such a fundamental area that it is extremely important for all chemists and all physicists, because so many things can be understood and so many theories are connected to them, and beautiful experiments today, experiments which go to what we call as a attosecond or a femtosecond. Femtosecond is 10 to the minus 15, 1 in 10 to the 15 seconds, 1 by 10 to the 15 second is a femtosecond. That's the time scale under which molecular vibrations happen. Typically, molecular vibration, one vibration takes place in a few femtoseconds, whereas attosecond, which is even lower in time, 1 by 10 raised 18 seconds, electronic transitions can happen, and we have attosecond spectroscopy, for which Nobel Prize was given this year or last year, I don't remember. But so spectroscopy is advancing very, very far, almost to the limit of measurements, and many molecular properties, many materials characterizations, many things that you need to know, and biological systems, everything can be studied using molecular spectroscopy. Okay? So that's the introduction I have. So if you have any thoughts, questions, and if you think that the lecture is clear or not clear, please, you have a minute or two to say some things. Then I will continue. Sorry, let me ask a few questions. எல்லாரும் எங்கேருந்து திருநெல்வேலியிலிருந்து எத்தனை பேர் வந்திருக்கீங்க? திருநெல்வேலியிலிருந்து யாருமே இல்லை. ஆஹா, என் சொந்த ஊருது. சரி, மதுரையிலேருந்து எவ்வளோ பேர்? மதுரை டிஸ்ட்ரிக்ட் யாரும் இல்லையா? ஒன்று. ஸோ சென்னை, ஐ சி யூ ஹேண்ட்ஸ், தேங்க்யூ. விருதுநகர், தென்காசி, கன்னியாகுமரி, கோவில்பட்டி இஸ் நாட் அ டிஸ்ட்ரிக்ட், தூத்துக்குடி கீழே வருது, தூத்துக்குடி டிஸ்ட்ரிக்ட். ஓகே, ஃபர்தர் அப் இன் தி நார்த், திருச்சி, தஞ்சாவூர், திருச்சி, ஓகே, தஞ்சாவூர், ஓகே. தென் அப்புறம் மீதி எல்லாரும் இங்கே வேலூர், இது இங்கே வந்துடுறீங்களா? இந்த மாவட்டத்துக்கு பக்கத்தில் வந்துடுறீங்களா? சென்னையிலேருந்து எவ்வளோ பேர்? சென்னையிலேருந்து ஒருத்தர் 2 பேர் தானா? சரி, ஒருத்தர் தான் வந்திருக்கேன். ஸோ விழுப்புரம், திண்டிவனம், விழுப்புரம். Yeah, I can see one hand over there. Okay. So, are you finding this program useful to you till now? Till now. Because you are going to be here for 15 days. And it's a long time. It's a long time to be away from home. And your classes begin as soon as you go back. Or maybe they would have started even before that, I guess. Yeah. College எப்போ ஆரம்பிக்கிறது? ஜூன் 15 ஜூன் 16. ஓகே, அதுக்கு கரெக்டாக ஒரு 2 நாள் கழிச்சு தான் போவீங்க நீங்கள் எல்லாரும் வீட்டுக்கு. ஓகே, ஸோ போன உடனே நிறைய வேலை இருக்கும். ஓகே, இது வரைக்கும் சொன்னது ஓரளவு கிளியராக இருக்குதா? ஏன்னா நான் நேரில் உட்காந்து பேசணுன்னு தான் எனக்கு ஐ வுட் லைக் டு டூ தேட். பட் நேரில் உட்காந்து பேசுறதுக்கு எனக்கு இந்த வருஷம் வாய்ப்பு இல்லை. இங்கே வர்றது, கனடா வர்றது ஒரு 3 மாதத்துக்கு முன்னாடியே முடிவு பண்ணிட்டோம். அதனால் டிக்கெட்லாம் வாங்கினதுக்கப்புறம் பிளான் எல்லாம் கேன்சல் பண்ணுறதுலாம் முடியல. ஆன்லைன் டீச்சிங் அண்ட் லேர்னிங், I did that for 3 years during COVID. I don't think I am very comfortable with that. But பரவாயில்ல, 10 லெக்சர் 15 லெக்சர்லாம் படிக்கலாம். ஒரு வருஷம் படிக்கிறது தான் கஷ்டம் ஆன்லைனில். A few lectures you can do. Okay? I would like to meet all of you when I come back sometime, but we'll not worry about that. Okay? So let's now get to the second part of the optical spectroscopy. Now I'm going to do a bit of mathematics. Okay? This is a theory course, and every one of you studied spectroscopy once, a little bit before, right, in your BSc. You have done rotation spectroscopy, you have done vibrational frequency, force constant. எனக்கு ஒரே ஒருத்தர் தான் தலையாட்டிட்டு இருக்காரு, மீதி எல்லாரும் சும்மா அப்படியே உட்கார்ந்துட்டு இருக்காங்க. Yeah. So எல்லாரும் படிச்சிருப்பீங்கன்னு நினைக்கிறேன். So let me quickly go through the first elementary model of spectroscopy in characterizing the phenomenon. This theory is due to Albert Einstein, who came up with this beautiful model of the 3 processes in spectroscopy called absorption of radiation, emission, spontaneous emission of radiation, and also stimulated emission of radiation. So I'm going to share my handwritten lecture slide. Okay? I will show this one page at a time, but we'll take time to go through each of these pages. Okay. Let's do that. Okay, so let me take the first image. So I'm not share. I need to share the screen. So now you are able to see the screen, right? It's called Theoretical Approaches to Understanding Spectroscopy. Are you able to read this? Yes? Okay. So let me just keep this up. Yeah. So this is what is called a phenomenological theory, or it's called a semi-classical approach. See, spectroscopy is fundamentally studied by quantum mechanical properties of the molecule. Spectroscopy led to quantum mechanics, discovery of quantum mechanics. So what is meant by semi-classical approach? What we do is that we treat the molecules as quantum objects. Molecules have energy levels, and we try to get the energy levels through solving the Schrodinger equation. And what we do is that we don't treat the radiation which interacts with the molecule, the electromagnetic radiation. We don't treat the electromagnetic radiation as photons. We don't quantize the radiation. We use the radiation as a classical wave, electric and magnetic fields oscillating in a wave-like motion and propagating. So we use the classical approach of the wave properties of light or electromagnetic radiation, while we use the quantum mechanical properties of molecular energy levels. So that is why this is called a semi-classical approach, and introduced by Albert Einstein. At that time when he did this, Niels Bohr's quantum theory and the Sommerfeld's quantum theories were available. Schrodinger's theory was not known when Albert Einstein proposed this. Schrodinger published this many years after. Okay? But of course, Albert Einstein followed all those things for many more years. So he envisioned three processes. Let's take a molecule with only two energy levels, E0 and E1. We'll only look at the small, localized two energy level. E0 is the ground state, E1 is one excited state. Okay. Now, how can you take the molecule from the ground state to the excited state? You can shine light, radiation. The radiation frequency should be the same as the energy, the radiation energy should be the same as the difference between the two energies, E1 and E0, which is hν. So you can see that the excited state energy is hν1, the ground state energy is hν0, and the difference between the two is hν, and radiation frequency and energy must match this hν. Okay? When it does, the molecule may absorb the energy and go to the excited state. This is called pure absorption. The second process is that whether the radiation is there or not, there are always a few molecules in the excited state. And there are also molecules coming to the excited state by absorbing energy. So some of these who are in the excited state can spontaneously emit radiation and come down to the ground state. This process is called spontaneous emission. Okay. So please remember, for absorption to occur, we need a large number of molecules here, and we also need radiation intensity. For spontaneous emission to occur, we don't need radiation, we only need molecules here, number of molecules, N1. And when the emission happens, radiation is emitted. the difference in energy is emitted as light. Now, the third process is molecules which are in the excited state are also interacting with the radiation, and due to the radiation, they may de-excite and come down to the ground state. In that case, for example, if a radiation falls on the molecule which is excited, and the excited molecule comes down to the ground state, energy conservation means that this photon must also come, and the photon corresponding to the transition from excited to the ground state should also come. So the stimulation is done by the radiation. The stimulated emission gives rise to more light, more electromagnetic radiation than before. So if there is one photon here, then there are two photons here. So this process requires a radiation density in addition to the number of molecules. So what Albert Einstein said was that these three processes follow simple physical laws with this kinetics. Okay? Molecules get excited, molecules get de-excited, then molecules get de-excited due to the radiation. So each one can be treated as a rate process. Now, if the radiation and the molecules are in thermal equilibrium, there is no net transition. Whatever the number of molecules which are created in N0, from N0 to N1, the number should come down to N0 again, and therefore there is equilibrium. So Albert Einstein came up with a small, very simple model equations. Okay, so let me go back to the second slide. So this slide explains what I said earlier, that stimulated emission is a transition induced by the radiation of the excited state of the molecule. Therefore, the result is the emission of two photons. And again, independently of radiation, molecules have a transition. So you can see that this is the spontaneous emission. So what is important here is these three processes occur under normal conditions with the system and the radiation in thermal equilibrium. So if the system and radiation are in thermal equilibrium, please remember the population ratio for the number of molecules in the ground to the excited state must follow the Boltzmann distribution law. Okay? Thermal equilibrium means molecules follow Boltzmann distribution. So the Boltzmann distribution should be followed. And so what is that process? So if there are only two states we are looking at, we will ignore all the other things. For a model, we need to understand what happens with the simplest model. So there are N0 molecules in the ground state and N1 molecules in the excited state. Generally, N1 is smaller than N0, unless there is a process called the population inversion has happened, which leads to the generation of laser light. We will not do that now. N1 is less than N0. And so you see that the energy levels are also non-degenerate. Then the ratio of N1 to N0 is given by the exponential of minus delta E by kBT. Delta E is the energy difference between the energies of the N1 molecules and the energies of the N0 molecules. So E1 minus E0, if you recall the previous slide. So delta E is equal to h nu, so it is e to the minus h nu by kt. Please remember, h nu by kt can be small or large. If you talk about microwave radiation or radio frequency radiation, h nu is very small even at room temperature and also small even at very low temperatures. So h nu by kt is extremely small. E to the minus x, that x is extremely small. This is approximately 1, which means almost equal number of molecules are there in both N1 and N0. Okay? Which means it's very difficult to excite molecules from the ground to the excited state because the difference is very small. So you won't get too much absorption. On the other hand, you go to electronic spectroscopy or vibrational spectroscopy, h nu is very large compared to kBT. Therefore, this exponential of minus h nu by kBT It's a small number. So what it means is that the number of molecules in the excited state are smaller, often much smaller than the number of molecules in the ground state. Therefore, N1 by N0 is a significantly small fraction of 1. And so you can see that it's possible to do by shining radiation. A lot of signal, lot of intensities can be generated if the molecule resonates with the radiation. And if there is a thermal equilibrium, the total number does not, N1 and N0 do not change. N1 increases but then decreases, N0 increases but then decreases. So you should say the rate of change of N1 with respect to time is the same as the rate of change of N0 with respect to time. Now, rates can be calculated using simple chemical formulas. Okay? One usually uses the concentration. So there are 3 processes here. Let us look at the N0 process and the N1 process. Okay? Next one. Okay. So we have to use first order chemical kinetics. Now, let me try to get both of them at the same time. Okay. Yeah, now you can see both of them together. Okay. It is important to see them together, and you can understand this. So N0 molecules in the ground state, N1 in the excited state. The rate of change of N0 is due to 2 things, or only one. Yeah, is due to 2 things. One is that N0 is changed to N1 by the absorption of the radiation. So the rate of formation of N1 is the number of molecules, N0 molecules, moving up to N1. That rate, dN0 by dt, is obviously proportional to the amount of molecules which are there, and also the radiation intensity. It's first order process, first order chemical kinetics. Rate is proportional to the concentration. The concentration here is 2. One is the molecule, the second is the radiation. So radiation concentration we measure by radiation density, which is MV, rho V. And this B is like rate coefficient. Okay? It's a phenomenological coefficient. B is a constant. What it says is that this is transition absorption coefficient to 1. The state 0 to the state 1. Okay, d0 to 1. So dN0 by dt is equal to N0 is V. Therefore, dN0 by dt is equal to the constant times N0 times rho V. So it is first order with respect to rho, first order with respect to N0. This is step number 1. Second step, the change in N1. N1 becomes N0 by 2 processes. One is the spontaneous emission. The spontaneous emission only depends on how many are here. Doesn't depend on the radiation because it's not there, it's not interacting. Therefore, the spontaneous emission component dN1 by dt is the coefficient A multiplied by the concentration N1. This is called spontaneous emission coefficient from state 1 to state 0. State 1 to state 0. Okay. But N1 also becomes N0 by another process, namely the radiation hits it. Okay? So if the radiation hits this, obviously the amount of radiation density will also contribute. So you see that dN1 by dt is also changing due to N1, the number of molecules in the state, and rho V, rho nu, the radiation density. And of course, together multiplied by a constant rate coefficient. So you can see this is like a second order reaction. Each one is first order with respect to the concentration. So the B10 is like a second order rate coefficient. Okay. Here also it is like a second order rate coefficient. Okay. First order with respect to N0, first with respect to rho mu, dN1. The thing is, in thermal equilibrium, both of these are equal. You can see what the meaning of A10. It's a spontaneous emission coefficient. B10 is stimulated emission coefficient from here to here. in the presence of radiation, 1 to 0. Then this is B, 0 to 1, which is absorption from 0 to 1. So these are the three rate coefficients and constants. So this is the equation between dN1 by dt and dN0 by dt. Now, the thing is, you also know N0 and N1 satisfy Boltzmann distribution, thermal equilibrium. Another important thing is this process of N0 to N1 through radiation, and this process N1 to N0 through radiation are two microscopically reversible processes. They are the opposite of each other. And there is a principle in chemical dynamics at the molecular level. It is called the principle of microscopic reversibility, which states that B1 to 0 is the same as B0 to 1. Phenomenon. Fundamentally, that is what is required. But A is different. The reason is A is not influenced by, A is this one. A is not influenced by radiation. Radiation influences the spot. So since A is different from B, but the two B's are the same, you have the next step, namely, this is what? This is 4. Yeah, next one is 5. Okay, so you can see the fifth one here. So now you can take the ratio N1 by N0. N1 is common here. Therefore, if you take N1, then it's the sum of A10 plus B10 rho V. That is this, A plus B rho V. I replaced the 10, removed everything. B is B and A is A, this one. So N1 by N0 is B rho V, A plus B rho V from here. Okay. N0 comes here, and the coefficients come on this side in the denominator. So now, what is rho V? Rho V is the radiation density. Radiation density, now if the whole thing happens in an isolated sort of a cavity-like thing, that is controlled absorption emission, then it follows very similar to the black body radiation law, which was the first thing that Max Planck came up with, and he gave a formula for the radiation density rho V by this particular formula to change the whole of physics. With this formula, he introduced the constant, Planck's constant, and the Planck's constant later on became the fundamental constant for all molecular systems. So the radiation density is 8 pi times h, the frequency of the radiation nu cube, divided by the speed of light c cube, times 1 pi exponential of h nu by kt minus 1. This is Max Planck formula for rho nu. And you know N1 by N0 also is given by the exponential formula. Okay. See, N1 by N0 is given by exponential of minus h nu by kt. Or if we want to do N0 by N, here N1 by N0 we have. So you can see that. So suppose we write N0 by N1, we do the reverse. A, B rho by P rho, this one. You are inverting N0 by N1. And N0 by N1 is exponential h nu by kt, because it's 1 by. N1 by N0 is this, N0 by N1 is 1 by, so it's e to the h nu by kt. Therefore, you can equate this to the A plus B. This is the formula for rho V, which you can introduce here. Okay? And then I want you to do the algebra and obtain as problem 1 the relationship between A and B. A is equal to 8 pi h nu cube divided by c cube times B. Okay? This is the first fundamental relationship through very simple approximations and very simple ideas that Einstein came up with. And the relationship between absorption coefficient and spontaneous emission coefficients can be actually verified in the laboratory and can also be derived by quantum mechanics. Exactly. Very rigorously, this relationship can be derived in quantum mechanics. So the beauty of this is that Einstein introduced the idea of the stimulated emission of radiation. Stimulation of radiation for excited state to come down to the ground state is something that was a fantastic idea that saw lasers almost 40 years before. Einstein published this in 2017, 1917 or 1918, around that period. Lasers were discovered in 1955, 56, and later 1960. So the stimulated emission of radiation, which leads to population inversion, that is, more molecules are in the excited state than in the ground state. That kind of population inversion eventually led to the discovery of lasers, and lasers today are so fundamentally important in all of our life. I mean, right from laser surgery to lasers in basic atomic and molecular physics and basic chemistry, lasers are everywhere. So the idea of Einstein is a fundamental notion to spectroscopy. Now, the more rigorous quantum mechanics, which was discovered later by Erwin Schrödinger, substantiated these relationships formally. And the next lecture, after a small break, because I think we have been listening for about an hour now, the next lecture, after 2 or 3 minutes, maybe 10 minutes late, we'll talk about only the Schrödinger equation, and we'll take you through some rigorous mathematics, but I also want you to remember the basic quantum mechanics as we go along. Okay, so let me stop here and stop sharing.
Swayam Prabha, Digital India, Educated India.